Dear students, welcome back. In the previous lecture, we had completed the method of power series. In this lecture, we are going to introduce the notion of Laplace transform and seeing some examples and see its advantages and its application towards ordinary differential equation. So this lecture and the next lecture will be about Laplace transform, and with this the course should come to an end. So let's motivate the idea or the need for Laplace transform. So usually when you have a differential equation, let's say suppose you have an ODE, what you have is that you have some function y and you have a differential equation corresponding to y, right? You have a differential equation in y. So there is a notion of Laplace transform which for a function y, it's going to give you, let's call it capital Y. You are going to get, so if this is a function of, so here if x is the independent variable, then you will have a corresponding function Laplace transform of the function y here. So the advantage of Laplace transform is that it will convert the differential equation to, which is in the function y. So it will convert this into an algebraic equation in capital Y. Okay, so basically to solve an ODE, you use the Laplace transform and then you have an algebraic equation in Y. Then you solve here for Y, and then you take the inverse Laplace transform, and then what you get is the resulting y, which will be the solution to this ODE. Okay, that's the advantage. So the advantage is that the differential equation, so now you no longer solve a differential equation. Using the transform, you move from this differential equation space to a space where the equation becomes algebraic, and if you can solve this algebraic equation, then you have actually, and if you can go back, that is, if you can take an inverse transform, then you actually have solved the differential equation. Okay, so we are going to see this technique in the next two lectures. Okay, so this is the definition of Laplace transform. So you are given a function f, okay, which is a function which is from the positive real line, and it is real valued. You are given a function f. So the Laplace transform of f, which is denoted as LF, okay, its symbol. So you have f. So you then have its Laplace transform, it's denoted as LF. Sometimes we also use capital F to denote the Laplace transform, but wherever possible we will use this notation. So we will use these notations interchangeably. Okay. Okay. So the script LF will denote the Laplace transform, or sometimes if you kind of capitalize the alphabet here, then that is the Laplace transform. Okay. Anyway, that will be clear from the context. So the Laplace transform of the function f is defined as this integral. So the Laplace transform, the independent variable is p, and that p is appearing here in this exponential here, and you are integrating over the x variable, so it's a function of p. Okay, so whenever this integral is finite, right, then you have a finite value for LFP. So for all p, this is valid. So in general, this Laplace transform can be seen as a function from the complex domain and it's complex valued. But in this particular course, we are not going to do it in that generality and so on. So for us, we can restrict the domain of Laplace transform to again positive real line and so on. Okay, so now how did we, I mean, what is the motivation for this definition? So see, natural thing is that the exponential is a good choice because exponential is one such function which kind of remains invariant under derivative, right? Because you know that d by dx of e power x is e power x, right? So if you have an a here, then it comes as a here and a here, right? So you have this property of this exponential that under derivative it becomes like this, and if you take product, so it just becomes sum of these exponents and so on, right? So in what you need to understand here is that this definition is nothing but the generalization of power series. Okay, one can view it like that. One can view this as a generalization of power series. For instance, if you, so let me just recall something about power series for time being. So you see, let's look at power series. Suppose I have a series like this: a power n, x power n, right? This is a power series, okay, and this is, so given a n, this is some function of x. So you can think of this, let's say this is f of x, okay. So what does this mean is that this basically means is that, so once I have a power series, so what determines this power series or this function are these coefficients, right? So what are the coefficients? So you have a0, a1, a2, but you have infinite number of them, right? So you have this collection of, so this collection of coefficients, right? And these coefficients correspond to the function f here, right? That is how the power, for instance, if you change these numbers here, you are going to get a different function and a different f, right? So in other words, if you kind of relate this with I mean a vector in say Rn, right? I mean, for instance, if I take an element x in Rn, you know that this has, any vector in Rn has this, in the Cartesian form, has this unique identification, right? So you have this coordinate corresponding to the vector x, right? If you take the Cartesian form, so these uniquely, so these x1, all these are real numbers, these x1, x2, xn uniquely determines the vector x, right? So that is an association. So in this respect, you can make a connection here that if you have a power series which is a function f, that f is uniquely associated by its coefficients. In other words, one can think of this as the coordinate system of or the I'm sorry, the coordinates of the f in some sense, right? It's in the power series sense, right? So now this power series is a discrete version. Why it's a discrete version? You see, these a0, a1, a2 are, can be thought of as functions again, right? This an can thought of as function, that is for n going to an, where this n is now coming from natural numbers. That's it, right? So this an is this association, and because this is the natural number set, this is a discrete set. So this is, which is why you have this CDC, I mean the sum here. So if I am looking for a continuous analog of the power series, right, what I should be writing is that instead of an, so for instance in this case one could actually write this an just to, I could think of an as a of n, which is same as an, right? For each n you have a number an, which is for each n you have a number an. So a of n is an. Okay, so you can think of it like this, and the domain is running from natural numbers, or in this case including 0. So let's take the whole numbers, right, including 0. Okay, so What is the continuous analog of this is that instead of n, now you don't have a discrete set, you take the entire real number. So just to not to confuse with this x, let's not use x, let's use t. Okay, so earlier you had the n, so n going to a of n. Now you have t going to a of t, and t is coming from real numbers. But in this case, since you started with positive integers, let's say positive line, let's say the positive real numbers. Okay, so t is coming from this, so now you have a function at, so you can replace this an by the continuous analog, which is at, and then x power t, right, x power t, and this, now you have a discrete sum here, so the continuous sum will be integral, the domain of n, which is 0, infinity, I mean natural numbers here it's the entire positive real line, so this. So now you see this again is a function f of x. This is the continuous analog of the power series, right? Now what you can do is that now you know that when you have x power t, an integral involving x power t, you know that this is not always finite, depending, so it depends on the value of x and so on. So for instance, you know that if x is between 0 and 1, then you can actually have that this integral is finite, because x power t is again something between 0 and 1 for all these t's. So this is fine. So when x power t, and you can think of x power t because as exponential of t log x, right? Because exponential t log x is precisely e power t, right? So this is, and in this case, and for log x to make sense, log x has to make sense when x is between 0 and 1. But you know that when x is between 0 and 1, so when x is equal to 1, this is log x, so log 1 is 0, and then when it actually approaches 0, it goes to negative infinity, right? So to kind of compensate for that fact, so log x is basically, so when x is between 0 and 1, log x is basically negative, right? Which means if I choose p to be log x, which is negative, then minus p is positive, right? And that's what we have done here. So what we do is we replace this log x by minus p. Okay, let's choose this as minus p. So minus p, so then p is positive. Okay, so in this case what we have done is this is same as e power t minus p, which is minus tp, which is what we have done here. So here whatever is x variable is now the t variable. Okay, so that, don't worry about that. So the point is, this integral here can be thought of as the continuous version of the power series. So it's in that sense, and this, just this observation, so, and more or less what you're kind of doing here is that you are thinking, I mean, so these f behaves like the coefficients at here. Okay, so that's the motivation for Laplace transform. Basically, this is the definition of Laplace transform. Okay, if you don't understand whatever I have just described, don't worry about that. If you can take the definition as a gift, I mean, as something like some God-given quantity, yeah, I mean you take it. But if you want the motivation I've explained is this, that the idea of doing this is to convert a differential equation into an algebraic equation. You will see that in the next lecture how we do it after we deduce the properties of Laplace transform. So that's the advantage of this. And how do we, I mean, then how did we know that we can do this? Is basically from the idea comes from the fact that we have the power series. So this is the kind of continuous analog of power series. More or less, exponential behaves nice with derivatives, and that is how we tend to replace this polynomial power here with in terms of exponential power. Okay, so that's the definition of Laplace transform. Okay, fine. Now let's look at some. What is the inverse Laplace transform? So Laplace transform is given by this integral. Inverse. There is also a proper definition of inverse Laplace transform, which involves, which is beyond the scope of this course. So as of now, as you can guess from the name, inverse Laplace transform is that function, right? So suppose you have a function f. The inverse Laplace transform is that function f whose Laplace transform when you take gives you capital F. Okay, that's how, right? So we'll just define it like this for time being, because that is what we will use in this course. There is also a much more general, I mean, a precise mathematical definition of inverse Laplace transform, but that we will not, like, we cannot define at this level. Okay, so what is inverse Laplace transform? If you have a capital F, the inverse Laplace transform of capital F is that function for which when you take Laplace transform, Laplace of f will give you capital F. Okay, that's the definition. Anyway, so now let's look at some simple examples. Let's take the constant function 1. So far, if you notice, the Laplace transform we have defined for function which is defined on the positive real line. Okay, and that is something which when we motivated we kind of, because we had, as we said, as the this was generalization of the power series, so we had from n0 to infinity, we went to the continuous version 0 to infinity. Okay, and it makes sense for x from this domain. Okay, that's what we will be using in this course. Okay, so let's take a constant function 1. So what is a constant function 1? So you are in the thing, so you are taking a constant function 1 like this. This is your f. Okay, what is the Laplace transform of this? So let's apply the definition. What is the definition saying? By definition, the Laplace transform of f, which is the constant function 1, is by definition 0 to infinity 1 times e power minus px dx, right? That 1 times is this. So you just have to integrate this. Now this is 0 to infinity, so you can think of this as limit r going to infinity 0 to r e power minus px dx, right? That's how you compute this integral. Now you just have to integrate this for each r. So for each r, if you do this, it's minus exponential e power minus px, right? So it's the integral of e power minus px, which is an exponential function, right? So that if you integrate, you get e power minus px over p with a minus sign with limits 0 to r, right? If you compute that, you see it's e power minus p power r over p plus 1 over p when you apply r. So e power minus pr. So this r limit gives you the first term here, and this 0 gives you the second term here. Now if when you apply limit r going to 0, so r is here positive, you see, because it's r is positive greater than 0, and as r goes to infinity, so r is positive, p is also p is fixed, right? P is, as we said, p we will be taking as positive. So in fact here if you see, the limit will exist only when p is positive, because when p is positive, minus p is negative, right? So minus pr is negative, right? So when r goes to infinity, this goes to minus pr goes to minus infinity, right, for each fixed p, right, minus infinity, which means this goes to 0. So when p is positive, this first term limit goes to 0. So you actually get 1 over p when p is positive. Okay, so in this case, the Laplace transform is defined for positive p's. So the domain of the Laplace, so the domain of the given function is positive real line, and the domain of the Laplace transform, so Laplace of 1 is also positive real line because p is positive and its real value. So if you actually look at the, so what you took was a constant function f, and the Laplace transform was the 1 over x function. So this is your capital F. So in this case the argument was x, in this case the argument is p. Okay, so this is one simple example. So the constant function, when you take the Laplace transform, becomes like 1 over p kind of function. Okay, it's actually 1 over p function, right? Now let's look at another simple example. So what are the next possible? So this is the constant function 1. Constant function 1 can be thought of as the polynomial of 0 degree. So next natural generalization is a polynomial of degree 1. Let's say f of x is equal to x, right? So in this case, for x positive, so this is the graph of this given function f. What is the Laplace transform of this function? So you apply the definition. So L of x is by definition x times e power minus x dx, right? So you do integration by, right, integration of this. So limit of r going to infinity 0p. So you do integration by parts. So it's x times derivative of this, right? So it's in the form of u v prime, right? Integration by parts. So when you do integration by parts, you get this with limit 0 to r. Now you do the same what we did in the previous example. Apply r. Okay, when you apply r, you will see that again for the same valid for all positive p, right? For all positive p, you will see that when you apply p equal to r, that term will go to 0. When you apply p equal to x equal to r, you will get as r goes to infinity, the numerator will be, go to 0, so it will vanish. And for the second term, when you put x equal to 0, so then the numerator has exponential of 0, which is 1. So there is 1 over p square here, but there is an x here. When you put x equal to 0, this term vanishes. So what you get is 1 over p square. Okay, so earlier for the constant function 1, we got 1 over p. Now for the function x, now for the function f, the Laplace transform turns out to be 1 over p square, right? Now what about x square, or let's say x cube, or more generally what about x power n? What is the Laplace transform of x power n? Let's see that. So more generally, for any natural number, the Laplace transform of x power n, you do the same argument, apply definition, apply definition. So you have x power n e power p px dx, this term, and this term has been written like using this term. So that's what we have here by definition. So now you apply integration by parts once. So you get this with an integral here, right? And this is something, again, the way we handled here, we can handle, right? So what you get, so here if you apply the infinity, there's a r here, it will go to 0. Then with the x equal to 0, there's x here, so this term will become 0, it will vanish, right? What remains is this n over p, and what is this is precisely the Laplace transform of x n minus 1, right? This is by definition Laplace transform of, so this should be script f, this is a mistake, so script f. So Laplace transform of x n minus 1. So you do the same thing that you did here, right? So now you have a recursive form. So if you keep doing that, you see that you will get another n minus 1 by p, so it becomes n minus 1 by p. Then what you get is Laplace transform script L of xn minus 2. It keep going on like this. Finally you will end up with n factorial over p power n, Laplace transform of 1. Laplace transform of 1 you already know, it's 1 over p. So the Laplace transform of x power n is n factorial over p n plus 1. Okay, so that's the Laplace transform of a polynomial. I mean x power n, degree n polynomial. Okay, now let's look at another simple example, which is the exponential. Okay, e power ax. What is the Laplace transform of exponential of ax? So let's apply definition. So in all these previous cases also, if you notice, all these are valid for p positive. Okay, so you start with the domain positive and it was valid for p positive. Now for exponential, you apply definition. You have e power ax, e power minus px, right? But they both are exponential, so it's the integral is just this. So it's e power a minus px dx. Now you can integrate this. So you limit of r going to of this integral of this quantity. Now you apply r. Then again, you will see that if you apply r, this thing will vanish as r goes to infinity only when a minus p is negative. And if a minus p is negative, it basically means that a is less than p. That means p has to be bigger than a. Okay, so for p bigger than, and the other thing, when you put x equal to 0, you get 1 over a minus. Okay, so if you apply limits, you get this. You take limit r going to infinity, what you get is 1 over p minus a, because of this negative sign here, which is valid for all p bigger than a. Okay, so that's what you so what is the Laplace transform of exponential? It is just this 1 over p minus a. So now you can think of it like this. So if you think of anyway, that's not the point now, it's fine. Okay, so that is the Laplace transform of exponential of a power x. Okay, now let's look at some more examples. Now what is the Laplace transform of sine ax? Okay, let's do by definition again. So Laplace transform of sine ax is integral sine ax e power minus px dx. So which is same as limit of r going to infinity. So you replace infinite r, which is same as this. Now you replace sine ax by its exponential, the complex form, right? The complex identity. The sine x is e power iax minus e power minus iax over 2i. Okay, and then e power minus px. Now since they are now exponential, you can bring them together, so you have this form. So 1 over 2i exponential of minus p minus p minus iax and exponential of minus p plus iax. Okay, you just sum them, right? Sum the exponents. So now if you integrate this, because now this is in the exponential form, if you integrate this, you get this form, limit of r going to r. So apply the limits and take the limit, right? So if you do that, then you get 1 over 2i, 1 over minus pi of this. So basically that limit corresponding to 0 will remain, rest will vanish. Okay. Okay, so once you have this you can simplify further. in the real form, so you actually have a real number. Though it looks like it's a complex number, but it's actually not a complex number, it's a real number. So the Laplace transform of sine ax is a p square plus a square. This again is valid for all positive p, because you need to use that when you do minus p times x and so on. Okay, so what is the Laplace transform of sine? So this a that appears here with in the sign is appearing here in the numerator and in the denominator here. Okay, so it's a over sine, a over p square plus a square, which is the Laplace transform of sine ax. Let's do another example. Let's do the cosine function now. So take the cosine function, apply the definition cos ax e power minus px. Do whatever we did in the previous example. This integral is limit of r going to infinity of this. Now you replace cos with the identity that you have, which is e power ix plus e power minus ix over 2. Right, now you bring the exponentials together. So now you have the integral of this exponential. Now you integrate them. So when you integrate them, you get a similar identity like before, except change in signs. Now you take the limit, apply for x equal to r, take the limit r going to 0, it will vanish. What you will put back is when you put x equal to 0, that will remain, that term will remain. So what you will get now for cos, the Laplace transform is p over p square minus. So for sine, you had a here in the numerator. For cos, you have now p. Okay, but the denominator is same. This is again valid for p greater than 0. So this is the Laplace transform of the cosine function. Okay, so now this is the so now the question comes down to, okay, we have defined what is Laplace transform. We have also found what is we have also seen examples on how to compute Laplace transform and so on. So far the examples that we have given were all continuous functions, right? It was the constant function 1, the polynomials s power n, and the sine function, cosine function. You can also extend the Laplace transform notion to piecewise continuous functions. But the basic question is, when can we find Laplace transform? Can we find Laplace transform to all functions? Right? What is the condition that should be satisfied by a function for the Laplace transform to exist? Right? This is a question that we would like to answer. So we are kind of heading towards that question. For that, let's look at this definition of what is called a piecewise continuous function. So what is a piecewise continuous function? It is a function where if it is continuous except at finite number of points, right? So something like, so what is a continuous function? A function something like this is a continuous function, right? And you have already seen a definition of what is a continuous function, which is in terms of epsilon and delta. So if you fix a if you fix some point here, let's call it f of x naught. So this is f of x naught plus epsilon and f of x naught minus epsilon, right? So then there should exist a delta So basically, if you see, what you get is a rectangle here, where this length is epsilon and this length is delta, which is centered at this point, which is x naught and comma f of x naught, right? So when you say continuous function, you have already seen this epsilon delta definition, right? So now what is piecewise continuous? Piecewise continuous basically means that the function is continuous, whereas this property, what we have shown here, this property breaks down at finite number of points, right? Something like, for instance, the constant function was continuous, whereas I can have a function like this. So this is a discontinuous function, right? Because up to this point it takes the value here, this one, and beyond this point it takes the value here, right? Now this is a discontinuous function, but this is a continuous function except at finite. So if you ignore this point, it's continuous everywhere. So this is piecewise continuous. This can happen at any finite number of steps. For instance, I could break it at multiple points. Okay, this is a function like that. In fact, one could also have a function like this. For instance, I could have a function like this and then like this. So so there is a break here, right? So these are all continuous functions except at finite number of points. Okay, so these are called piecewise continuous. So you have finite number of segments in which the function is continuous. Okay. Let's look at another definition of what is called a function of exponential order. Okay, so when do you say a function is of exponential order? If there exists an alpha and an x naught and an m. Okay, so there are three quantities, alpha, x naught and m, such that for all x bigger than x naught, mod fx is less than m e power x. What this basically means is that e power minus alpha x is bounded. That's what this means. So in fact you can, so this is positive, you can say this. So you say a function f is of exponential order if you multiply that function by e power minus alpha, right, minus alpha x, that function is bounded. That's what this definition tells you. So then you say the function is of exponential order. Okay. Okay. So if you want some examples of functions of exponential order, all bounded functions are exponential order with alpha equal to 0, right? Because if a function is bounded, it basically means you can find an m such that mod f of x is less than or equal to m, which means this inequality is valid with alpha equal to 0. So it's a function, so any bounded function is exponential or with order alpha equal to 0. Now x power n is an exponential function of for any alpha bigger than 0. Right, so for any choice of e power n, you can actually have x power n is so the x power n is bounded. Okay. So if you look at limit of this, so when you want to show bounded, you need to show e power minus alpha x power n. This is bounded, right? This is what we need to show is bounded. But as x goes to infinity, it actually goes to 0, so it has to come down, and so it has to be less than some m, because it finally falls down to 0. And why does this happen? Because this is a function which tends to 0 as x goes to infinity, right? Because it's negative power of exponential, and that goes to 0 faster than polynomials, right? So it is an exponential, so this goes in the exponential rate, whereas this is in the polynomial rate, right? So this goes faster to 0, so this limit goes to 0, which means it has to be bounded. So x power n is a function of exponential order, and this is valid for any positive alpha, right? Because for minus e power minus alpha x to go to 0, this exponent should be negative, right? And if x is positive, then alpha has to be positive as well. So here we have taken x to be positive. Okay. Now exponential of x square is not of exponential order. So this is a function which does not fall under this category. Okay. And why does that happen? Because if you look at this function exponential of x square minus alpha x square, basically multiply the given function by e power minus alpha x, which is this is unbounded for any alpha. right? Because it's exponential of x square minus alpha x. So whatever choice of alpha you take, x square minus alpha x is always this exponential of this is always unbounded because it's the exponential of some positive power. So now let's come to the original, the theorem that we were interested in, that is the result. When do we have Laplace transform? So if you have a function f which is piecewise continuous in every closed interval of R, right? Every closed interval 0a, okay, and of this form 0, 0, comma. So the domain is the positive real line, but if you restrict your domain to any positive a and look at the interval 0a, in that closed interval the given function is piecewise continuous and it is of exponential order, sorry, and it is of exponential order, say alpha, then the Laplace transform exists for p greater than alpha. That's the theorem. Okay, so the function has to satisfy two conditions. One condition is that it has to be piecewise continuous in this domain for every interval, so for every choice of a positive, and the function is of exponential order of some alpha, then the Laplace transform exists for p bigger than alpha. Okay, so let's give a proof of this result. So because it is given that f is exponential order, this is satisfied. So there is an x naught, there is an alpha, there is an m, such that for all x bigger than x naught this happens. This is by definition of the exponential order. Okay. Now let's look at the Laplace transform of f. Let's just define, so by definition, let's look at that integral. So Laplace transform of f is integral e power minus px fx dx. Okay. Now we can split this into two integrals around this point x naught, which is coming from the exponential order definition, exponential order property. So you take the integral from 0 to x naught and x naught to infinity. Okay. Here, so you split the integral into two integrals. Now we need, if we show that this sum is finite, then we are done. This, of course, there is no problem with this integral. So we need to show that this integral is finite here, because this is already, it's a finite interval, and you already know in this interval 0a, so 0 x naught, this is a piecewise continuous. Okay, so you can actually, this is a finite integral because it's a bounded function now here, because it's a continuous function on a closed interval, it is f. So what remains to be checked is this second term here. Okay, this I have already said. The first integral is finite due to piecewise continuity, right? Because f is continuous on a closed interval, so f is actually bounded. So this is actually a nice integral which you can compute, which is finite. Okay, so it cannot blow up. This is finite. So what is this? So look at the second integral, x naught to infinity e power minus px fx dx. Now this is less than or equal to this quantity, and how do you get that? See, for any number x is less than or equal to mod x, right? So if you take this is less than or equal, this is less than or equal to mod of this, and that is less than or equal to integral mod of whatever is inside. Which is precisely what you have here. Okay, so this integral is less than this integral. But mod fx, you know by the property that this is of exponential order, is e power minus alpha x, e power alpha x times m, right? Is less than or equal to m times e power alpha x. So we just substituted this with e power alpha x m. So you have this integral. Now m is just a number, it's independent of the x variable. So what you're integrating is this exponential function here, right? So if you integrate this, we have done this multiple times in this lecture now. If you integrate this, and the first term will vanish if this p minus alpha is positive, which is why precisely you had the condition that p has to be bigger than alpha. So if that happens, so for p bigger than alpha, you have this quantity, which is a finite quantity. So which means that this integral is finite, which means the Laplace transform exists. Okay, so what is this theorem has given you? So this theorem has given you an assurance that we don't know whether the Laplace transform exists for all functions. What we know is that if the function is piecewise continuous on the interval 0a for for all possible a, and if it is of exponential order, then the Laplace transform always exists. Okay. So since we have already said that the piecewise continuous function also admits a Laplace transform, let's as an example compute the Laplace transform of a piecewise continuous function. So this is an example of the Heaviside function. Okay, Heaviside function, this is function. So here we have taken a, so a is positive, greater than or equal to 0. So let's pick a here. So what is, and the domain of this is positive real line. So domain is always positive real line. So for x less than a, the function is 0. So it's 0. And for x greater than a, the function is 1. So let's say 1 is here. So this is a piecewise continuous function, right? Step function. Okay. So this is the Heaviside function. Now when a is equal to 0, when a is equal to 0, h0 of x is precisely the constant function 1, which we have already computed. Its Laplace transform is 1 over p, right? That's just the constant function 1. But when a is strictly greater than 0, then you have a piecewise continuous function. What is the Laplace transform of that? So let's compute. So as I have already observed, so when a is 0, this is equal to 1. So the Heaviside function is a constant function 1. So the Laplace transform is 1 over p. When a is strictly bigger than 0, let's compute the Laplace transform of h of a, which is 0 to a e power minus px. So the value of value of ha when x is less than a is 0. So you have 0, and then otherwise it's 1. So you have 1 here. Okay, so this integral is 0. So what remains is this, which is a infinity. If you integrate that, you get this, which is valid for p bigger than 0. We have done this before, right? So for p greater than 0, you have e power minus a power p. So the Laplace transform of a piecewise continuous function here is e power minus a power p over p. And this is also valid when you put a equal to 0, you get 1 over p. Okay, so let's look at, to make one more observation about inverse Laplace transform. Let's make an observation. So look at this function, which is a piecewise continuous function. So what is this function saying? If you plot the graph of this function, is when x is from 0 to 3, so let's say this is 1. Okay, this is 1 and this is 2. So when x is from 0, let's say this is 3. So when x is from 0 to 3, the function takes the value 1. So this is the value is 1. Okay, and when at x equal to 3, so till less than 3, so strictly less than 3, up to just Up to 3 the value is 1. At 3 the value is 2. And when x is bigger than 3 the value is again 1. Now this function is also piecewise continuous. Right? It's piecewise continuous. It's discontinuous only at the point 3. Otherwise it's continuous. So it's piecewise continuous function. What is the Laplace transform of this? Let's compute that. What's the Laplace transform of this function? So Laplace transform, if you compute this function, up from 0 to 3 it's 1, so you get this first integral. Okay, and from 3 to infinity it's again 1, so you get this integral. Okay, so this is playing no role. The value of x equal to 3 is not playing any role because it is observed here. So from 0 to 3 it's here because integral doesn't have to. 0 to 3 it's 1, and then again 3 to infinity it's 1. If you compute, put them together, what you get is 1 over p for p bigger than 0. If you do the integral of this, you can see that, right? It's basically 0 to infinity of e power minus px dx, which is 1 over p. So the Laplace transform of this function is 1 over p. Now please recall, what was the Laplace transform of the constant function 1? That was also 1 over p for p greater than 0. Right? So now what is the Laplace? Suppose I look at the inverse transform of, because that's how we define inverse transform, right? Inverse transform is that function to which when you apply Laplace transform you get the given function. So inverse transform 1 over p, is it 1 or is it this function? So there are two possible values, so which means the inverse Laplace transform is not even well defined, right? So for one function there are two possible values. So this is also an example to tell you that you have the same Laplace transform for two different functions, right? But are they really different functions? They are different functions, yes, because a constant function takes the value 1 at x equal to 3, whereas this function is taking the value 2. So they are different functions because the value at one point is changing. So they are different functions, but their Laplace transform is 1 over p, and that's happening because Laplace transform is defined in terms of integral, and integral does not seem to see the change in value of the function at one point. Okay, so the idea behind this example is to tell you that two different functions can have the same Laplace transform, right, in general, which basically means the inverse Laplace transform is usually not well defined, whereas we will state it here. This is something which we have already said. So compare the above example with the constant function 1, and that's what we have done, and we see that they both have the same Laplace transform. So the inverse transform 1 over p is not necessarily unique, right? One of the inverse transform was the constant function 1, which is continuous, whereas the other inverse transform was this function, which is piecewise continuous. In fact, I can find more. If I introduce more number of finite number of discontinuities in this function further along in x greater than 5, for instance, I put for x equal to let's say 4, f of x is again some value 100, doesn't matter. You keep doing this till the Laplace transform will be 1. As long as I introduce finite number of discontinuity to this function or to the constant function 1, this Laplace transform won't change. So you have more than one inverse transform for 1 over p, right? But what we know is that one of the inverse transform is continuous and the other are all not continuous. They are all piecewise continuous. So there is a result which tells you about the uniqueness of continuous inverse Laplace transform. That is, in general, the inverse Laplace transform is not unique, but if you are looking for a continuous inverse transform, that is, the inverse transform of the function has to be a continuous function, then there is a unique inverse transform. For instance, for the inverse transform of 1 over p, there are many, but if you are looking for a continuous inverse, a continuous functions whose transform is 1 over p, then that is 1 only. Every other function whose Laplace transform is 1 over p will be a discontinuous or piecewise continuous function. Okay, and this is true for every possible function. So this theorem tells you that the continuous inverse transform, if it exists, so it may not exist, that is one. If it exists, then it has a unique continuous inverse transform. Okay. So now with this, we will stop the lecture. So the next lecture we will derive more kind of further properties about Laplace transform and also show the application of Laplace transform on an ordinary differential equation and how it converts it into a algebraic equation and so on. Basically how to solve an ordinary differential equation using Laplace transform. Okay, see you.